So we're going to talk about absolute maxes and absolute mins, or global maximums or global minimums today. All right, you guys can all see the screen, hopefully, and hear me. So we're gonna get going with this here. An absolute maximum for a function on an interval just means that every single other point on that function is less than that y value. And an absolute minimum is the exact opposite. It means that every other point is larger than that minimum value. Easy enough. That's what a max and a min are. That should be pretty, I think, self-explanatory, pretty straightforward. If we talk about an absolute maximum within the domain of an interval, we can look at the endpoints and we can look at points in the middle of it as well. Same with if we're looking at the minimum values. Hold on one second here. I gotta answer my kid's question. All right, sorry about that. And no, he was not coming to ask for fruit snacks this time. He was coming to have me check his math homework because I forced him to make, to let me check the math homework. Otherwise, it's no good. You didn't show me the last problem.
Well, I did it correctly.
You did it correctly? Okay, good enough. He says he did the last one right, so we'll assume he did. All right. Where were we? Maximum, minimum. Oh, okay, so if we're going to talk about an absolute maximum of the sine function, specifically on the interval 0 to pi, what would the absolute max be? And not max like my child, maximum. What would the absolute max on the interval 0 to pi of sine x be?
1.
Should be 1. Absolute max is 1. And where does it occur? At x equals pi over 2. So if the question is just what is the absolute max, the answer is 1. And then oftentimes they want to clarify where does that occur. So make sure you don't put pi over 2 as the max. That's the location of the maximum, but the maximum is actually 1. What about the absolute min on that interval, on the interval from 0 to pi of sine x? What is the absolute minimum of sine x between x equals 0 and x equals pi?
0.
Should be y equals 0. And where should it occur? At x equals 0 and at x equals pi, right? It's okay that those are the same, that there's two different locations of this absolute minimum, because we have less than or equal to or greater than or equal to, right? So it's okay if they're equal to each other. What about for the cosine function? What is the absolute max on the interval from 0 to pi?
1.
1. Where? At x equals
0.
0. And what about the absolute min?
-1.
At x equals pi. Yeah? Everybody good with that? All right, everyone's good with that? And no, Yaya, my other child is not named Min. What a terrible, terrible joke that was. All right, let's specifically look at a function then here, like f of x equals x squared, and let's investigate the absolute max and the absolute min on different intervals. So we're going to start with the interval from -infinity to infinity. And we're going to see if it has to have a max, it has to have a min, and what they are. So what about an absolute minimum on the interval from -infinity to infinity of the simple function f of x equals x squared? What's the absolute minimum?
0.
0, and where does it occur?
0.
Good, and you can see that it's just the vertex of the parabola, right? What about a max? Is there an absolute maximum between -infinity and infinity?
Well, there's no maximum, it just keeps increasing.
Right, it just keeps increasing, so there is no absolute max. What about the closed interval from 0 to 2? Is there an absolute minimum?
Yes.
Yeah, it should be 0, right? Still at x equals 0. What about an absolute max?
Or
Should be 4, and it should be at x equals 2. All right, what if we changed this so that we no longer had a closed interval on both sides, but that on one side we had an open interval on the 0? What would that tell you about an absolute min? Would it still be 0 at x equals 0?
no, it would just be really close.
No, it would just be really close. And we can't get to 0. And so we would say there's no absolute min. But what about the absolute max? Should it still be 4? Yes, it should still be 4. Exactly. So we have an absolute max of 4 at x equals 2. And what if we went in and we changed this all together and just made these both open intervals? I would have no absolute max or min. Everybody agree with that? Any issues, problems, questions, complaints about that? No, everyone's good. All right, spectacular. So that's going to sort of lead us into something called the extreme value theorem. And the extreme value theorem says that if we have a function that is continuous on a closed interval from a to b, then there must be an absolute maximum and there must be an absolute minimum on that interval. But that's only if it's a closed interval and it's continuous on the entire closed interval. Okay, this is called the extreme value theorem. So for the top 4 graphs here, I know I didn't draw endpoints on them here, but we're going to say that the function is continuous on the closed interval from a to b for all of these. So does this first one have an absolute max? It should. It's a closed interval. It should be up here. And the absolute min should be down here. Agreed?
Yes.
All right. Both the absolute max and the absolute min are on the interior of the domain from A to B. What about the second one? It has an absolute min here and an absolute max up here. True? Hopefully.
Yes.
Yeah. And we'll note that one of the absolute things, the absolute minimum, was at an endpoint, but the max was not. So we could have one or the other. Same here. The min is at an interior point, but the max is at an endpoint. Or theoretically, we could have both endpoints be the max and the min. Good or no? Hopefully that's good. Hopefully, right? So all of those are continuous on the closed interval A to B, and they must have a max and a min. What about the bottom one? This one's not continuous, right? Not continuous on A to B. And therefore, we're not guaranteed to have an absolute max and an absolute min. It doesn't mean that we can't. We still could, but it doesn't mean that we are guaranteed to have one. And just because we get very close to whatever this y value is up here, let's say that y value is 10. That does not mean that that is our absolute max, because we don't actually get there. We get to 9.9999999, and then we jump down here. And the discontinuity means that we no longer have to be guaranteed to have that absolute max or absolute min. Good? Make sense?
Yes.
All right. So now we're going to make a quick distinction between an absolute max or min and a local max or a min. So a local maximum or a local minimum, like we were talking about with our graphs of the derivative the other day, a local max or a local min just has to be the highest point on some open interval surrounding that point. Right? So as long as I can draw any open interval surrounding that point, and it's the highest point on it, then it's a local max. Or if I draw any open interval surrounding some other point, and it's the lowest point on that interval, then it's a local min. Okay. The same applies for endpoints. This endpoint at A is a local min because I can have a half open interval from A to whatever this point is here, where it's the lowest point. Same at E. Right? I can have a local minimum at E because on the half open interval, it's the lowest point. And we'll note that an absolute maximum or an absolute minimum can also be a local, right? Or a local one can also be an absolute. Okay. Good or no? Everybody good? Everybody up to speed on local, absolute, maxima, minima, and what they are? And if you looked at a graph, you could see what they looked like at least. Figure out what they were based on a graph, I hope. Yes, no, maybe, yes? Oh, good.
Wait, so an absolute extreme value is just for the whole domain of the function.
That's correct. That is correct. All right. So what we're going to do now is we're going to talk about when we can find local maxima and local minima. So we already talked about a local maximum or a local minimum occurring when the derivative was 0. True? Like when we had those graphs that we were doing yesterday, we saw that every time we had a local max or a local min on our graph, the derivative was always equal to 0. True?
Yes.
Yeah, so that's a possibility, that when the derivative equals 0, we might have a local max or a local min. It could also occur when the derivative is undefined, like at a cusp, right? Or at a corner. We could have a local minimum or a local maximum. You guys agree with that? You see that's the case, yeah? Hopefully.
Yes.
All right, cool. So what we call these points where the derivative equals 0 or where the derivative is undefined is a critical point. These are called critical points or critical values. Okay? And so a critical point or a critical value is just a value, an x value at which the derivative is 0 or the derivative is undefined for a function. And a critical value or critical point is the only point at which a function might have a local minimum or maximum on the interior of its domain. So I cannot have a local min or a local max inside of the domain of a function unless it's at a critical point. Good or no? Good or not?
It's good.
All right, I mean, think about it. If I'm trying to draw a graph, how else can I get a local maximum other than a place where the derivative was 0? Or a local minimum unless I had a corner or I have a cusp, right? I'm not going to be able to get a place where I have a local max or a min without one of those things occurring. So what we're going to try and do now then is we're going to try and find the absolute maximum and the absolute minimum of a function on a closed interval from -2 to 3. So we're going to try and find the absolute max and the absolute min of x to the 2/3 on -2 to 3. So first off, we know that an absolute max can occur at endpoints of a closed interval. True? Do you guys agree with that? We said that up here, right? We could have them at the endpoints of a closed interval, absolute max and absolute min. And we could also have the absolute max at an interior point on the domain, right? Like we saw over here, at an interior point of our domain, we could have an absolute max, or we could have an absolute min, or we could have both on interior points. So if we're looking for the absolute max and the absolute min of a function, we have to check two different things. We have to check all the critical points, and we have to check the endpoints if it's a closed interval. Does that make sense, what we're going to try and do then? Hopefully.
Makes sense.
All right. So first off, let's find the critical points. Find critical points by finding the derivative. So what's f prime of x? What's f prime of x?
Two-thirds x to the negative 1/3.
2/3 x to the negative 1/3, which could be rewritten as 2/3 cube roots of x. True?
Yep.
All right, cool. When does this equal 0? That'd be some of our critical points, right? When that equals 0?
It wouldn't equal 0?
It will never equal 0, right? It does not ever equal 0 because it only equals 0 if the numerator equals 0 and 2 doesn't equal 0, right? So when is it undefined? It's undefined if what part equals 0?
The denominator.
Denominator.
If the denominator equals 0. So when does that equal 0? That'd be at x equals
0?
at x equals 0. Exactly. So we only have one critical value. This is our only critical value or critical point. But we also need to check the endpoint. So we'll go and see what's f of -2. We'll figure out what's f of 0. And we'll figure out what's f of 3. And whichever one is the largest is our absolute max on that interval. And whichever one is our smallest is the absolute min. And whichever one is neither of those, and we can forget about it. So what's f of negative 2?
The cube root of 4?
Cube root of 4. Right? Square the negative 2 is 4, and then cube root it. What's f of 0?
0.
0. And what's f of 3?
The cube root of 9?
Cube root of 9. Which of those is the smallest? And thus our absolute min? 0, right? 0 is smaller than positive numbers. So an absolute min of 0 at x equals 0. And an absolute max of what? Which one's the largest?
Cube root of 9?
Cube root of 9. And that's at x equals 3. Everybody good with that? Does that make sense to everybody or no? All right, so let's start taking a look at this one. Give me 1 second. For some reason, my child is climbing a ladder and trying to get on the roof or something. I'll be back in just a second. Okay, sorry about that. I'm not sure. He's trying to put up Halloween decorations or something. I don't know. He's climbing on the ladder. I looked out the window and he's like almost on the roof. Maybe I should just let him climb up. All right. We good? Are we ready to start this next one?
Sure.
Sure, great. All right. We want to find the extreme values of 1 over the square root of 9 minus x squared, even though for some reason it doesn't look like 1 over the square root of 9 minus x squared. Now it does, much better. All right, so what are we going to do with that? First off, what should we probably try and figure out? The domain? I was going to say the domain because there's no endpoints given to us, right? So we should probably check and see what the domain is. And generally, you always want to try and investigate the domain of a function if you're looking for maxima and minima of it. So what's the domain of this?
Negative 3 to positive 3?
Should be from negative 3 to positive 3, right? Because 9 minus x squared has to be greater than 0. It can't be 0 because it's in the denominator, and it can't be negative because it's inside of a square root. So we've got x squared is less than 9, or x is less than 3, greater than negative 3. Right? So there's our domain. So any critical values that we might find that are not on that domain, we can just ignore because they're not part of the domain of our original function. And then the second thing we'll do then is take the derivative. So f of x is 9 minus x squared to the negative 1/2, right? So what's the derivative become? Should become negative 1/2, 9 minus x squared to the negative 3/2 times the derivative of 9 minus x squared, which is negative 2x. Or what? X over 9 minus x squared to the 3/2. So when does that equal 0?
When x is 0?
Okay. When x is 0. When is it undefined? For a lot of values, probably, right? because I can't square root any negative values, right? And I can't have a 0 in the denominator, but is this going to be undefined for anything that's within its domain? No, it's never undefined on the interval -3 to 3, right? So the only critical value we get is x equals 0. Everybody good with that?
Yes.
Okay. So if our critical value is x equals 0, then that means that we can only have either an absolute max or an absolute min. We're not going to have both. And how will we determine what it is? Well, first off, let's find what f of 0 is. What's f of 0? One-third, right? And how do we know if that's a max or if that's a min?
By testing points around 0?
Yeah, we can just test a point to the right of 0, something between 0 and 3, right? So like, what's f of 1? F of 1 is 1 over root 8. Well, which one is larger? 1 over root 8 or 1 over 3?
1 over 3. Wait, no, 1 over square root of 8.
Yeah, 1 over root 8 is larger than 1/3. So we have an absolute min of 1/3 at x equals 0. Good or no? Yeah, no, maybe, yes, no. All right, we'll assume yes. All right, so one thing that I want you to keep in mind is that just because you get a critical point, or just because you have an endpoint, it does not make it an absolute extrema. Okay, so if we were looking at the absolute extrema for y equals x cubed, and we tried to take the derivative and set it equal to 0, we'd get that x is equal to 0, right? But does x cubed have a max or a min at x equals 0? No. Same thing over here. Y prime is 1/3 x to the -2/3. And this is undefined at x equals 0. But that function looks like this, and it does not have a max or a min at 0 either. Right? So you have to still check and test to make sure that your critical values are actually extreme. Good or no? And we're going to learn tomorrow, especially, a bunch of ways to test, but we're going to do some today as well. So far, good or no? Yeah,
Yeah.
still alive there? Okay, good. All right, so let's take a look at this one. We're going to find the extreme values of this piecewise function, 5 minus 2x squared, if x is less than or equal to 1, and x plus 2 if x is greater than 1. Any thoughts on how we'll start this?
Find the domain.
All right, thinking about the domain. So first off, we've got x is less than or equal to 1, x is greater than 1. So theoretically, that should encompass all real numbers, right? Can you plug in all numbers that are more than 1 into x plus 2? Should be able to, right? So that's good. And can you plug in any number less than or equal to 1 into 5 minus 2x squared? Also, you should be able to do that, right? So our domain is negative infinity to infinity. So all we then need to do is figure out critical values for this because there are no endpoints. since our function is split up into two different pieces, let's do one for when x is less than 1. We're not going to do one at 1. We're not going to say or equal to 1. We'll deal with that in a little bit because that's where our breaking point is. And so we got weird stuff happening there. But if x is less than 1, what is f prime of x equal to?
-4.
Negative 4x, yep. And when does that equal 0? If x is 0? And is it ever undefined? No, it is never undefined. All right, and then what about if x is greater than 1? What's the derivative? What's f prime of x?
1.
1, and that does not equal 0 ever, and it's also never undefined. So the only potential critical value we got from looking at things less than 1 and greater than 1 was only x equals 0. And the x equals 0 fell into x is less than 1, so that makes sense. So we've got a critical value of x equals 0. Now, let's look at what happens when x equals 1. For us to have a derivative that is defined at x equals 1, the derivative from the left, or negative 4x, needs to equal the derivative from the right, or 1. Well, does that happen at x equals 1? Does negative 4 equal 1? No. So at x equals 1, f prime is undefined. And so we'll have another critical value at x equals 1. So a place where the derivative was 0 was at x equals 0, and a place where a derivative was undefined was at x equals 1. Good or no? Any issues or questions on that?
Can you explain why the derivative from the left has to equal the derivative on the right?
So in order for the derivative at 1 to exist, where we have the break in our piecewise function, you have to have the same slope on both sides of 1 meeting up at 1. So the function would have to first be continuous at 1, and then it would have to have the same derivative from each side at 1. And so it's continuous at 1, because if you plug in 1, you get 3 to both of them. But the derivatives, negative 4x and 1, are not equal to each other when x is 1. And so the slopes of the tangent lines as you come in from the left are not the same as the slopes of the tangent line as you come in from the right, and they're not even approaching the same value. And so therefore, the derivative can't exist at that point. Does that make sense? Does that help?
Yeah, thank you.
Yep. All right, so we got two critical values, 0 and 1. So let's test them to see what the value of our function is. What's f of 0?
Five.
5. Okay, and what's f of 1?
3.
3. All right, and so then how else are we going to figure out? Obviously 3 is not the absolute max. 5 could be the absolute max. How are we going to determine if it is? Or if it's just a local max? Any ideas? What happens as our x values go towards negative infinity? What's the limit as x approaches negative infinity of f of x?
It also approaches infinity. Negative infinity.
It approaches negative infinity, right? Because if I plug it into 5 minus 2x squared, a large negative number, will become 5 minus infinity or a negative infinity. So we know that as we go towards negative infinity, it's going to be decreasing forever, which means it's never going to go back above 5, right? Let's look about the limit as x approaches positive infinity of f of x. What happens to that?
It approaches positive infinity.
It approaches positive infinity, which means that my x values, as they get larger, are giving me y values that get much larger than 5. So is 5 an absolute max?
No.
No. And is 3 an absolute min?
No.
No. So we don't have any absolute extrema. So we'll say no absolute max or min. But we do have a local max of 5. And where does that occur? At x equals, what was it? X equals 0. And we have a local min of 3 at x equals 1. Does that make sense to everybody? Any questions or that on that, or is everybody good there? All right, let's do one more problem. I'll be back in 1 second. So take a look at this one. Think about what you're going to do first, and I'll be right back. Okay, sorry about that. I just heard a large crash a couple minutes ago in my garage and wanted to make sure that neither of my children were dead. Turns out they're not. So good news. All right. We all set? We all ready?
Yep.
All right. So how are we going to deal with this one? Extreme values of natural log of the absolute value of x over 1 plus x squared. What's the first thing we should do?
Find the domain.
Find the domain. What's our domain?
I'm pretty sure all real numbers.
You're missing one. So first off, the denominator of this, 1 plus x squared, can't equal 0, right? That doesn't give us any real solutions. But we also can't take the natural log of negative numbers and of 0. But any negative number that we might get inside of here is not going to matter because we're taking the absolute value of it. So the only thing is that x over 1 plus x squared also cannot equal 0, which would be when x is 0. So we're leaving 0 out of the domain. That makes sense to everybody?
Oh, yes.
Okay, cool. So if we happen to get a critical value of 0, then we can ignore that because 0 is not in the domain and we can't have an extreme value in a place for a function that's not defined. Good or no?
Wait, so why is it undefined at 0?
Well, you can't take the natural log of 0. Right? If you plug in 0 for x, you get 0 over 1, which is 0. And then the natural log of 0 is undefined.
All right. Okay.
Yep.
Are we ignoring like that the denominator can't equal 0?
Well, 1 plus x squared doesn't equal 0 means that x squared can't be negative 1, which there's no real solution to, x squared equals negative 1. So
Yeah, thank you.
yeah, 1's positive, x squared is always positive. Add them together, and you're never going to get 0. So, okay, now what do we need to do? We need to take a derivative, right? Well, we don't have a rule on taking a derivative of something with an absolute value, do we?
No. So do we split it up?
Yeah, we can split this up. So we're going to say if, in fact, I'm going to do this in a different color so things don't get too convoluted here. If x is greater than 0, what can you tell me about x over 1 plus x squared? It should also be greater than 0, right? Because the denominator, no matter what x value I plug in, is going to be positive. True? And if I plug in a positive for x, then the top's going to be positive also. So if x over 1 plus x squared is greater than 0, then what is the absolute value of x over 1 plus x squared equal to? It's just equal to itself, right? It's equal to x over 1 plus x squared. So if x is positive, then f of x is equal to the natural log of x over 1 plus x squared. And how do we find the derivative of that? Using the chain rule and the quotient rule. F prime of x should be, so this is natural log of u, so it should be 1 over u. Well, what's 1 over a fraction?
The reciprocal.
Yeah, it's the reciprocal of it. So we have 1 plus x squared over x, and then times the derivative of x over 1 plus x squared, which comes from the quotient rule. 1 plus x squared times 1 minus x times 2x over 1 plus x squared squared. And we can cancel some 1 plus x squareds, right? To give us an x in the denominator and a 1 plus x squared in the denominator and a what in the numerator? 1 plus x squared minus 2x squared, so 1 minus x squared. Everybody good with that?
Oh wait, shouldn't the for the quotient rule, shouldn't it be x times 1 plus x squared minus the 1 plus x squared?
For the quotient rule, it should be the denominator 1 plus x squared times the derivative of x.
Wait, the denominator is x though.
No, denominator is 1 plus x squared.
Oh, sorry.
No problem. All right, everybody good with that derivative now? So it equals 0 if x equals 1 or negative 1. And when is it undefined? If x equals 0. And what is the piece of the domain that we're talking about here? We're just specifically talking about x being greater than 0. So ignore x equals negative 1 and ignore x equals 0. So the only critical value we get from doing the right-hand portion of this is x equals 1. Everybody good with that so far?
Yeah.
All right, what about if x is less than 0? If x is less than 0, then x over 1 plus x squared is less than 0. And that means that the absolute value of x over 1 plus x squared is equal to the opposite of x over 1 plus x squared. Everybody agree with that based on the definition of absolute value that we talked about earlier this year?
Yeah.
All right, so now f prime of x should be, well, it should end up being almost exactly the same, right? The only difference between these two functions, I'm sorry, the natural log of the negative of that. The only difference between those is just the negative sign, right? And so if I'm doing 1 over u, well, that's 1 over this again, right? It's just the same thing. 1 plus x squared over x with a negative in front of it. And if I'm going to do the derivative of the inside of it, it's just going to be the exact same thing again, except with a negative out in front of it. Right? Because the derivative of a constant times a function is just the constant times the derivative of the function. And so this should still end up being 1 minus x squared over x times 1 plus x squared squared. And we end up with the negatives cancel. 1 minus x squared over x times 1 plus x squared, giving us the exact same values, x equals 1, -1, and 0 for undefined. Good or no? We could still ignore x equals 0 because it's not in the domain. And for x less than 0, now we'll ignore the 1, and we'll just have another critical value of -1. Does that make sense to everybody? So we have critical values of x equals positive and -1. Any questions or issues with that so far? I know we're dragging on here. We got 10 minutes to go. We're almost done. Everybody okay with that or not?
Yes.
All right. So first off, let's figure out what f of 1 is and what f of -1 is. So what's f of 1? Natural log of what?
Natural log of 1/2.
Natural log of a half, and same with -1, right? It ends up being natural log of a half also. So these are either absolute maxes, or they are absolute mins, or they are local maxes or local mins, but we're not going to have one of each. And so let's do the same thing we did before by looking at the limits as x approaches infinity and -infinity of our function. So the limit as x approaches infinity of absolute value of x over 1 plus x squared. Well, how do we figure that out? We do the natural log of that. We do a u substitution. We'll let u equal the absolute value of x over 1 plus x squared. And as as x approaches infinity, what does u approach?
0.
It should be approaching 0. And since it's inside absolute value, it should be approaching 0 from which side? The negative side or the positive side?
The positive side?
Right. If my u values are always positive, I can't approach 0 from the left. I have to approach 0 from the right. So this becomes the limit as u approaches 0 from the right of the natural log of u. And what is the limit as u approaches 0 from the right of the natural log of u?
-infinity.
-infinity. Good. So we know that to the left, to the right, as we go towards infinity, our function is dropping and getting smaller than it would be at natural log of a half. And then we could hopefully do the same thing with -infinity. So let's think about this. If we do the same substitution where u is equal to the absolute value of x over 1 plus x squared, well, as x approaches infinity, the inside of this is still going to approach 0, isn't it? And to take the absolute value of it, it should still be 0 from the right-hand side. And so that should still be -infinity. So as our function goes towards infinity and as our function goes towards -infinity, it's dropping off lower than natural log of a half is. We also had a discontinuity at 0, so we also need to look at that. So let's look at the limit as x approaches 0 from the left of the natural log of the absolute value of x over 1 plus, oops, 1 plus x squared. As x approaches 0, what does the inside of this become? What does x over 1 plus x squared become as x goes towards 0?
Yeah.
Becomes 0. And from which side, because of the absolute value, is it approaching 0? Should still be from the right. And so we should get negative infinity. And what if we do the limit as x approaches 0 from the right of this? It should still come out to be negative infinity, right? Because the same thing's going to happen if I substitute out this absolute value of x over 1 plus x squared. It's still going to be approaching 0 from the right of natural log of u, which is negative infinity. So what does that tell you about the values natural log of a half and natural log of a half at 1 and negative 1? Are they maxima or are they minima, first of all?
Max.
They're maxima. And are they absolute or are they local maxima?
They're absolute.
They should be absolute because everywhere to the other sides of them, we are dropping off. So an absolute max of natural log of a half at x equals positive or negative 1. And real quickly, I'm going to open up Desmos, and we're just going to take a look at what this graph looks like before we're done. So natural log of the absolute value of x over 1 plus x squared. And this is what this function should look like. We said that we've got these maxes at negative 1 and 1 of natural log of a half, which is that value, negative 0.693. And as we go to the left, it drops to negative infinity, slowly, but it still drops to it. And as we go to the right, to infinity, it drops. And as we go to the left towards 0 and to the right of negative 1 towards 0, it drops also.
Actually, we can't see the screen.
Oh, spectacular. Now you can, yeah?
Yes.
All right, let me try that whole spiel again then. So at negative 1, we have the max of natural log of a half, and to negative infinity we drop, and towards 0 from the left-hand side we drop. And same from 1, as we approach 0 from the right we drop, and as we approach positive infinity we drop. And so therefore those are absolute maxes of the graph. Does that make more sense now that you can actually see the graph, rather than me just rambling about it without the graph sitting there?
Yeah.
Oh, good. Any questions on that at all, that whole process?